All right, Dan, thanks for the kind introduction. And as Dan mentioned, I'll be talking to you about hydroxy radical footprinting methodology that we've developed internally in collaboration with Immunoscientific. So at the end of this presentation, I hope I can make a case by saying that analyzing structural changes upon aggregation can be a strategy for resolution. So to give you an outline of my talk, it'll be two parts. First, I will give you an introduction to hydroxy radical footprinting methods known as plasma-induced modification of biomolecules, or PLEM, which is a proprietary technology that was developed at Immunoscientific. I will go over the PLEM that's used as a structural tool to understand the dimerization of an antibody, which is a bispecific antibody. I'll describe some of the PLEM workflows that we've adopted to analyze these dimers, as well as the data analysis tools that are available for PLEM. Next, I will show you a case study where we've developed this method to look at the aggregation of a bispecific antibody. We'll show general workflows and how PLEM has been used to assess the oxidative modifications on these bispecific antibodies. And then by using this information, we can propose the mechanism for aggregation of these bispecific antibodies. So first, to give a general introduction, is manufacturability of a drug is a key component of the drug discovery and development process. As we know, manufacturable drugs must maintain safety, efficacy, as well as they has to be of high quality and stable at scale. So issues with manufacturability, such as aggregation, may not be apparent until they are highly concentrated during process development stage, after all of the R&D has been completed. This really jeopardizes years worth of R&D, the effort and the cost that you put. So we believe that aggregation issues should be addressed much earlier during discovery and not at a later stage during development and manufacturing. So we have used aggregation, a bispecific antibody that was prone to aggregation, which had a single chain variable fragment and which was having high levels of aggregation during cell line development. So cell line development actually sits between discovery and development phases at Janssen, and we undertook the effort to investigate the dimerization. So our initial hypothesis is that structural changes are precursors for dimerization. Secondly, structural changes and regions on dimer interface can be mapped effectively using a technique that I'm going to talk to you. And then the mechanism of aggregation can be understood and then mitigated from really understanding the mechanism. So the platform we've used here is to analyze purified monomer and the aggregate, in this case a dimer, in its native state in solution, and mapping structural changes across the entire antibody, not just limited to certain regions, and then inferring where the binding is taking place in this dimer. So we identify the antibody-antibody dimer interface by comparing the dimer to its monomer. It's a binary comparison. So here's the PLEM platform that was used for these footprinting experiments. And this is, again, a proprietary technology that's offered as services through Immunoscientific. Here, the footprinting, unlike most footprinting methods, hydroxy radical footprinting methods, you have to add hydrogen peroxide through Fenton's chemistry. Here, we are using a plasma source to ionize molecules in air that will eventually lead to the generation of radicals directly from water. So it's a sub-microsecond burst of radicals that are generated through this plasma. And we can accurately and repeatedly introduce this plasma through this feedback mechanism, and it's completely controlled by a computer, and it can also do 96 samples in about 30 minutes. The type of radical modifications that are induced through this technique include the oxidation, typical oxidation modifications, dioxidations of cysteines and methionines, and in addition to the typical modifications that we observe with other types of HRPF methods, cysteine has trioxidations. And nitrosylation is very unique to this technique, where nitrogen and oxygen in the air produce the nitro radicals. In addition to these, we have the CF3 precursors that we can add to the solution to generate CF3 radicals, which will give a more comprehensive map of these modifications. And this type of analysis is very helpful for residue level analysis. So the technique starts with a native protein in solution, and we are labeling the protein in its native state and capturing the conformation through these labels. So these labels are irreversible, and therefore what takes place subsequently to this labeling does not perturb or does not disrupt the information that was captured in the labeling itself. So you can use any type of protease that can digest this protein into surrogate peptides that can be used to then measure the amount of modification on each of these peptides. So we do that by mass spectrometry, and through different types of fragmentation, we can generate fragments that can be mapped back to the protein sequence. Not only can we identify the sequence, but we can extract the chromatograms for each of these peptides, the modified and the unmodified counterparts, and then we can calculate the percent modification, which is an indication of the solvent accessibility. So it's again a binary experiment. In here we are showing two states of the experiment, where state 1 is the apo form and state 2 is the hollow form of this myoglobin molecule that was analyzed. And through the differential expression or differential analysis of oxidation, we can then use this site-specific information to map them to a linear structure or a three-dimensional structure, as shown here, and then complete the experiment. So with this experiment, we are looking at the native state in solution assessment of these molecules. We can obtain both peptide level information as well as residual level aggregation site mapping, identification of not just the aggregates, but also even higher order structures such as multimers. And we've actually, in fact, looked at beyond the dimers, trimers, and even tetramers. This analysis can be typically completed in 1 to 2 days, and we only need 50 to 100 micrograms of total protein to complete this analysis. So it's high throughput, limited samples, and the complete analysis is end-to-end, and the completion takes a very short time. Here's where we've applied this to looking into this bispecific antibody. This had a single chain variable fragment. So you can see the analytical approach is PLEM, but in this molecule we have a heavy chain 1, which is the CFE, and the heavy chain 2, and the light chain of that is the Fab domain. Through other experiments, we've also confirmed the formation of the dime, and we believed at the time going into these experiments that the aggregation was happening through some sort of a domain stopping mechanism on the CFE, and we wanted to actually validate them through these experiments. So the data analysis is also streamlined. Once the data is collected, it can be automatically swept into this vendor agnostic software known as BIOS through Protein Matrix, who's also one of our collaborators, that can analyze this data quite readily using their built-in footprinting workflow that's found in this software. So the modification levels are calculated using this formula, and it's the modification to the total sum of the modified peptides and as well as the unmodified counterpart of the peptide. And we can also, in this software, can remove any type of artifactual modifications that can happen during ionization, like in-source oxidation. This software also ensures that the correct extracted ion chromatograms can be generated for individual peaks as well as sets of peaks where the modifications can be more pervasive across the entire sequence. And the third feature, very importantly, is not all peptides fragment in the gas phase due to the stochastic nature of fragmentation. So in silico peptide analysis is critical to rescue peptides or extracted ion chromatograms that you see to be differentially expressed or presented but don't have a MS2 identification. So that's the third feature of this software. In addition to peptide level analysis, important feature is to do residual level analysis using additional reagents such as the trifluoromethyl label and the CF3 precursors actually get a radical to the transfer of these free radicals from the hydroxyl groups. And you can see to your bottom right-hand side, the table, you can see when we do hydroxyl labeling, you can modify 5 of the 20 amino acids. With on average for antibody, it's about 15% of the total protein gets these labels, and which is about 6.3. The average length between the modifications is about 6.3 amino acids. So it's not a residue level analysis. But when you combine this with CF3 labeling, you can improve the coverage to about 40%. And we can see that the average length between the modifications is about 1.6. Now, when you combine the analysis with hydroxy radicals as well as CF3, the coverage goes up to about 50% with almost near residue level resolution for this type of analysis. So where do we actually use this? Is when we need more granularity, like epitope mapping experiments that are shown here, where we've combined hydroxy labeling as well as CF3 labeling to look at the epitope of the HER2 epitope, one of the 3 loops where we can see that there is statistically significant difference in certain residues, alanine 586 and cysteine 587, which were identified by 2 different types of modifications. One was a hydroxy label, and in the other case, it was a CF3 label. And in some cases, like histidine, where it's susceptible to both hydroxy labeling as well as CF3 labeling, you can get information from both these labels. So in the second half, I will describe how we've applied this technology to look into bispecific antibody aggregation. So just a disclaimer here is this antibody and the antibody-derived products that I'm going to show today were derived directly from culture supernatants. And we see high levels of aggregation of these multispecific antibodies during their expression. So at Janssen, we've developed and engineered a new class of bispecific antibodies that are stapled. So the stapling is between the linker and the VH and VL domain using cysteine bridges. And these cysteine staples actually have improved the properties of these multispecific antibodies to be more stable. They also maintain binding affinity when compared to the unstable version, as well as they're functional, and also they show minimal aggregation due to heat stress and high concentration compared to the SCFE counterparts. So this is the general workflow where we are performing this PLIM experiment to understand the mechanism of aggregation between these bispecific antibodies. So we start these experiments by using purified samples of the monomer and a purified sample of the dimer. Then we subject them to 10, 20, and 40-second plasma doses, and we perform these in replicates. Perform this digestion using various types of proteases, and I'll show you how we've expanded this workflow to examine other types of enzymes. And then we subject them to LC-MS and perform the data analysis using the protein metric software that I spoke to you. So it's a complete streamlined workflow, which is end-to-end. Here's a peptide map of the heavy chain 1, which is the single chain variable fragment. And you can see using trypsin, you get somewhat comprehensive coverage, but there are certain regions of the chain, heavy chain 1, that lacks peptide reads. So this could be really problematic when we are doing these hydroxy radical footprinting experiments, because we need very comprehensive coverage across the entire molecule in order to look into its structure. So the modification levels are assessed through this estimated using this equation, which is showing is looking at the intensities of the peptides of the modified species normalized to the intensity of the unmodified peptide counterpart to the sum intensities of all the peptides that contain modification, in this case oxidation. A better way to address these coverage issues is to use additional proteases in combination with trypsin. And that's what Immunoscientific has done here, is to add the second enzyme along with trypsin, which introduces these non-specific cleavages in addition to the highly specific cleavages that you get from trypsin. This produces very short reads along the entire molecule, and we get 100% coverage. But as you may note, the diversity of the peptides creates additional problems. But we think that using all these peptides, we can do a more comprehensive estimation of the modification levels by doing a residue level modification estimation, as shown in the equation below. So using this technology, we can actually, combination of enzymes, we can actually do residue level without even having the need for CF3 type of labeling. So here's the result that we get for the heavy chain 1, which is a volcano plot of all the peptides that we identified. And what's shown here is the y-axis is the confidence of our analysis, is the negative log of the p-value for the t-test difference that we're doing, which is the log twofold change between the dimer to monomer ratio. So anything above a p-value, negative log a p-value of 1.3 is a p-value of 0.05. So we are looking at a statistical confidence of less than 0.05 for all these peptides that we are quantifying. So anything that's up in ratio is peptides that were modified, and they were having increased solvent accessibility or exposure to these free radicals. And from this analysis, you can see at the top right-hand side, above the p-value cutoff, you see 3 peptides that span regions of the linker and the VH of the single chain variable fragment. So with this analysis, we can tell that these residues were susceptible to oxidation in the dimer relative to the monomer. So another way of looking at this data is to actually plot the fold change or look at the modification levels between the two states, the monomer and the dimer, across the entire molecule from the N-terminus to the C-terminus. So it's no different than the volcano plot, the only difference being that you can actually spot them very closely and you can see them in a linear format. And you can see again the 3 peptides that was alluding to earlier, 1 on the linker and 2 on the VH domain. So I'll tell you the importance of these in the subsequent slides. But we didn't end up just looking at heavy chain 1, which had the single chain FV, but we also looked at the Fab domain. And looking at the Fab domain, we see opposite trends. It's actually a mixture of different things happening. So one is where we see decreased solvent accessibility upon dimerization on the Fab domain by 2 peptides. And then in another peptide, we see a slight increase in solvent accessibility. So again, we can represent this kind of mapping again in this linear format from the N-terminus to the C-terminus, where we see these changes between the monomer and the dimer. So then we went and looked at cysteine-specific modifications that we get in the footprinting data. And what we're seeing here is the cysteine di and tri-oxidations, as well as, in addition to that, we saw in certain regions where tyrosine was nitrosylated. This is the only modification. This is a unique modification that's only seen in the PLIM data. No other footprinting method can provide this kind of granularity and modification. Nitrosylation is normally not observed in other methods. So you can see regions 3, 4, which is the single chain FV region, linker, and the VH domain respectively. And you can see that these regions were exposed to solvent in the dimer relative to the monomer. In addition to that, region 7 is the FC region, cysteine, which also had high levels of oxidation in the dimer relative to the monomer. So making use of this information, we try to use other types of analytical data to validate our footprint. They can validate each other. And we've used disulfide mapping experiments to confirm the presence or absence of certain cysteine disulfides. So that's what we've done here, is going back and looking at the disulfide mapping data. We can see, we compare both monomer and dimer disulfide maps. And you can see that cysteine 119 to cysteine 237 bridge in the dimer is relatively low compared to the monomer, which indicates that those bonds could potentially undergo some sort of scrambling. And we also examine the trimer in this case that even goes up even higher. So in addition to the disulfides, we can also see cysteines that are cystinylated or exist as free thiols, which is also indicated that those disulfide regions are either scrambled or exposed to solvent. And we believe that the dimer is therefore, dimerization is happening at these regions where the link and the VH domains are opening up due to the breathing motion of the CFE, which we call conformational dissociation, and that allows these antibodies to form these aggregates. That's the current hypothesis we have on this dimerization, and we can actually propose a very, initial, a mechanism on how these could possibly form. So we believe that the folder monomers can attack each other on the SCFE domains, and the SCFE domains then undergo partial domain swapping, not complete domain swapping, because we only see unfolding happening between the VH and the linker. Where the VL domain and the linker stay together, we see this using our footprinting data, and we also see this using our disulfide data, mapping data. So we think that this intermediate stage is where the dimerization is taking place, and then complete domain swapping, which has been proposed earlier for these single chain Fe fragments, is not completely happening, at least in this molecule that we've examined. So taking this kind of two-dimensional mechanistic view of aggregation, we can actually say that these some of the conclusions that we came up with. So there's no signs of protection on the heavy chain 1, VL, linker, or VH, suggesting that there's only partial domain swapping dimerization. Increased labeling in the linker and the VH is consistent with the cysteine disulfide mapping data, and decrease in the cysteine 119 to cysteine 237 disulfide bond suggests that that's the case, and we also see high levels of cystinylation on 237. And also there was no changes in the VL labeling, suggesting that there is no VL, unlike VH, stays in contact with its linker. So taking this information, we can actually perform or refine molecular dynamics structural models using molecular dynamics simulations, which I won't have time to go through. And this is kind of our next evolution to these techniques, is to refine these models using footprinting data and other types of high-order structural MS data. So with that, I would like to acknowledge my colleagues and team at Janssen, as well as our collaborators in Immunoscientific, and especially Dan, who is in the audience actually. I forgot to include his name, but actually it was one of his presentations that I borrowed in this presentation. So his name is not there, but Dan's in the audience, and big thank you to you and Immunoscientific for the great work and partnership that we've had with Janssen, and also Protein Metrics for being such a really good collaborator over the years. We've been collaborating with them and developing software tools for biopharm for the past 6-7 years. And without these collaborators, we wouldn't be able to take our research to the next level. And with that, I'd like to thank you for your attention and open to any questions.
Great talk, thank you. I've got colleagues at the University of Leeds doing fast photochemical oxidation of proteins with hydrogen peroxide who dream of being able to get their end products in 1 to 2 days. It's taking them months to analyze the data. Are you aware if the Proteometric software can cope with hydrogen peroxide-based radicals, or do they have to stem from plasma or synchrotron radiation?
Yeah, absolutely. Yeah, it can analyze any type of labeling. So they got a workflow for, it's the same workflow that we've used that they have for any type of labeling. So it could also have do HDX. So if you want, you can do hydrogen deuterium exchange experiments, which has its own built-in workflow. It's just a node with suitable parameters to kind of interrogate that kind of data. So if you have different label, you can just simply include this as a dynamic modification. If it's not hydroxyl, if it's something else, you can do that quite easily. Yeah.
Cool, thanks. And then second, just a quick naive question. So it's obviously known that hydroxyl radicals are preferred to react with certain amino acids, such as the aromatics methionine. With the CF3 radicals, is it completely promiscuous, or does it still have a certain amino acid preference?
I don't quite know, so it's known to react with all 20 amino acids. So the degree to which it modifies may be dose dependent, and that's pretty much controlled by the software and the controls that are implemented in the PLIM technology. And they do multiple levels of dosing, like, so that's the 10, 20, 40 second total exposure times that I showed in the previous slide in the workflow. But each of those experiments done using submicron microsecond dose bursts of plasma. So so it's very, very well controlled, so there is no denaturation or structural perturbation that's happening. So yeah.
Thank you.
Hi, thanks for sharing the nice data. I'm just wondering if you made a follow-up experiment trying to optimize your molecule to avoid dimerization, if you succeed.
Yeah, so there have been a number of follow-ups, and we've been working closely with Nutrascientific with follow-up molecules, follow-up changes in structure, which we have not disclosed. And of course, our stapling technology platform has really mitigated a lot of these issues. But there's definitely further improvements that we need to make. And I think, footprinting methods really help to address those problems that we are seeing, even with changes that we make during engineering of these molecules. Yeah.